Hey guys, we are going to keep talking about water right now. We talked a lot about the various properties of water in the last lecture, and we're going to keep talking about water. We're going to focus on water as a solvent. Water will form a solution with many materials, and again, this is because of hydrogen bonding. And a solution is any time that you have a homogeneous mixture of two or more substances. Um, and when you use certain terms when you talk about a solution, so you would talk about a solvent being the dissolving agent or the material in the greater quantity. So for the examples that we're going to be looking at, water is the solvent. And then you're going to have the solute, which is the substance that is being dissolved, or the material in the lesser quantity. So if you were going to, let's say, make a glass of salt water, water would then be the solvent, and then the salt would be the solute. And so when we talk about materials that will dissolve in water, what we're talking about are hydrophilic materials. And hydro meaning water, and then philic meaning that means to like or to love. And so we call them hydrophilic materials because these are materials that will actually interact with water in order for them to dissolve. And so these are going to be materials that have ionic or polar regions, and then they can interact with hydrogen bonding with water. So here we have an example. So you've got one large kind of chunk of salt down here, and you can see that you've got the water starting to interact with the sodium and the chloride from the salt, and it's going to start to break it down, like if you wanted to make salt water. We also have hydrophobic materials that we're going to talk about, and these are materials that repel water. So again, hydro meaning water, and phobic in this case means to fear. And so these are going to be materials that do not interact the same way with water, so they're not going to dissolve or break down. Examples would be lipids. So a really classic example is when you mix oil and water, the two will stay separate because oil does not like water, it is hydrophobic. So when you're looking at solutions, a lot of times you want to talk about solution concentration. And this is going to be based on the molarity of the solution. And the molarity is simply the number of moles of solute per liter of solution. And just a quick review, moles are the molecular weight of a substance in grams, and then one Avogadro's number of molecules. So that's going to be 6.02 times 10 to the 23rd. What you're looking at here is 1 mole of each of those substances. So what you should keep in mind is that 1 mole, again, is always going to be that molecular weight of a substance in grams, or it's going to be a certain number of molecules. And so because molecules all have different sizes, 1 mole of copper is going to look very different than 1 mole of something like sugar. So water will actually break down on its own, and we call that the dissociation of water. And so what that means is it can actually split into 2 ions. So here we have a molecule of water. We have 2 molecules of water. You can see they're interacting with a hydrogen bond right here. And what's going to happen is the hydrogen, one of the hydrogens from this water is going to actually move over, and it's going to form the hydronium ion right here. And then we also have a hydroxide ion over here. So in pure water, the concentration of each of these ions is going to be 10 to the negative 7. And so when we look at this, we're going to start talking about pH. So adding certain solutes disrupts the balance between the 2 ions, meaning that it's not going to be equal anymore. And so the 2 ions are actually very reactive and can drastically affect a cell. And so you guys have, I'm sure, heard about acids and bases. So acids are materials that can release more hydrogen ions. An example would be hydrochloric acid. You guys see acids in nature when you look at things like acid rain. So you can see here that this statue has sort of been kind of eaten away over the years because it's been exposed to acid rain. And then you've got bases, and these are materials that absorb hydrogen ions. And so they reduce hydrogen ions by producing hydroxide. And so the example here would be sodium hydroxide. And then you've got neutrals, and these are materials that aren't acids or bases. When we talk about pH, we're looking at a logarithmic scale that shows the concentration for the hydrogen ions. And so we've got here a diagram showing certain things on the pH scale. So if you look at 7, you've got pure water, and things like human blood are very neutral. As you go, actually it looks like you're going up, but the numbers are getting smaller here. As the numbers get smaller on the pH scale, you're looking at more acidic solutions. So gastric juices or stomach juices are going to be very, very acidic. Whereas then if you look at the basic end, things like oven cleaner and household bleach are going to be very, very basic. So for a neutral solution, you're going to have a pH of 7. And then acids, again, are going to be anything that are pH of less than 7, and bases pHs greater than 7. Keep in mind that because we're looking at a logarithmic scale, each pH unit is actually a 10 times change in that hydrogen ion concentration. But when you look at the amount of hydrogen ions and the amount of hydroxide ions, should always add up to 14 when you're looking at the concentration. So if you know the concentration of one of the ions, then you can easily calculate the concentration of the other. Again, this is just showing you essentially the same idea, where you've got neutral pH, and so you have equal amounts. I know it's kind of hard to see. You have equal amounts of hydrogen and hydroxide ions, but as you go higher on the pH scale, or I'm sorry, lower really, this is the acidic side, you have more of the hydrogen ions, fewer of the hydroxide ions, and then vice versa down here as you get basic. And then we've got something called buffers. Buffers are important because these are materials that have both acid and base properties, and they help resist pH shifts. So cells and other biological solutions often contain buffers to help prevent damage. All right, so your summary for Chapter 3. You guys should be able to discuss the properties of water. You should be able to measure solution concentrations in molarity. And you should also be able to work questions based on the pH scale. All right, so your lecture question. So in your own words, can you explain to me, providing examples, why buffers are important, especially to biological systems? So please make sure you provide an example in your answer. All right, thanks guys.